All right, here we go. So we're doing our day 2 notes on probability. Day 1, if you missed it, it was pretty simple, like a review of probability from previous classes. We talked about the probability of single events happening, such as the probability of rolling a 2 on a die. Today, we're going to talk about compound probabilities using and or. For example, the probability that you roll a 2 and then a 3. Or conditional probabilities using given. And here it's talking about rounds of March Madness. We will get to that as we get closer to Selection Sunday for that. All right, so 2 events are independent events if one does not affect the probability of the other. So I'm going to say independent events don't affect the probability of the other. Okay? And when 2 events are independent, if you want to find the probability of them both happening, you multiply the proportions. Is that dark enough? Multiply proportions. Okay. There's better color. All right, so an example of that would be when you flip a coin twice, those are 2 independent events. What you get the first time has no effect on what you get the second time. So an example of independent events would be flip a coin twice. The probability of getting tails and then tails is 1/2 times 1/2, which is 1/4. All right, dependent events affect the probability of the others. So that means once one thing happens, that affects the probability of the other events. So affect the probability of the other. And I'm going to write this, but I'm going to explain it better with an example. So you multiply, but you subtract 1 from the total for the second proportion. I'm going to give you a minute to write that down, and then I want to talk about the example. Okay, so our example is a drawer that has 5 red socks and 3 blue socks. So what's the probability that you choose a blue sock on your first draw? 3 out of what? 3 out of 8, that's right, because there are 8 socks altogether. So the first time you take a sock, it's 3 out of 8. Now, you have a blue sock, you already took that sock out of the drawer. What's the probability that the second sock is a blue sock? No longer 3, it's what? 2, very good. And it's out of 7 because there are only 7 socks. So the probability that the first sock is blue, the second sock is dependent on that, because now one of the blues is already taken, so that would be 2 out of 7. So that would be 5 out of 56. Okay? And we should get used to expressing these probabilities as percents too, so you can do that just by dividing your fraction. 1/4 is hopefully one you can do in your head. That's going to be 25%. That was up here. 25%. I'm going to do 5 over 50. Oh, did I say 5 over 56? Nobody stopped me. What is that? 3 times 2 is 6. Okay, so 6 out of 56, which is 3 out of 28. I don't even trust myself. You guys need to check me. Is that right? Alright, so I'm dividing. 3 out of 28. So I'm getting 10.7%. Okay, what question do you have about that? Alright, so now we're going to talk about when you have two events, so they would be called A and B in this case. The probability of A and B, you might remember when we talked about Venn diagrams, this was and. So that means both events have to happen. Alright, if both events happen, do you remember how we shade that on a Venn diagram? Both things are happening. What part is that? Outside? Who said middle? That was right, thank you. So both events are happening. Here's event A, here's event B, and they're both happening here in the middle. Okay, if we want to do the probability of A or B, we write it this way. It's one or the other or both. And in terms of numbers, when we're calculating probabilities with the Venn diagram, what you're going to do is you are going to add the probability of A plus the probability of B. But there's a problem, because if we add A and we add B, how many times did we count this part in the middle? Yeah, we counted it twice. So we don't want to count it twice for a probability. That's a problem. So we're going to subtract it once. So minus the probability of them both happening. That's how we get rid of that problem where we counted it twice. So the probability of them both happening, you'll remember, is the Venn diagram with both circles shaded. And you shade it all. Okay, We say two events are disjoint if they have nothing in common. So, let's see, what could be disjoint? Trying to think of two things that you could do one or the other, but not both. So, you could have prob stat second period, or you could have PE second period, but you couldn't have both second period, right? So those two events are disjoint, having prob stat second period and having PE second period. So let's write the definition. Have nothing in common. Should probably open my pen. And that means that the probability of both things happening is 0. And if there's nothing in the middle, if this here is 0, then we could say that the probability of A, U, B is the probability of A plus the probability of B. And that's only because the intersection of them is 0. Alright, and then the multiplication rule for independent events, we actually already used that up here for the coin flip. To find the probability of both things happening, you just multiply their probabilities. So if they're independent, then the probability of A times the probability of B is going to equal the probability that they both happen. Alright, so these rules can be kind of tricky when we're not talking about examples, so we are going to talk about an example right here. First one says, of the 31 people on a bus tour, 7 were born in Virginia and 5 were born in Maryland. So the first question is, are V and M mutually exclusive events? So look back for your examples. Do we have mutually exclusive? We don't, do we? What's that? Oh, disjoint. Thank you very much. So yes, mutually exclusive would be disjoint. Let me just put that up here. Disjoint events. What do you guys think? Are they disjoint events? Yeah. Can you be born in both Maryland and Virginia? No. Okay. So we're going to say yes, they are. I'm going to write disjoint because it's shorter. Because you can't be born in both states. All right, so the probability that you were born in Virginia is going to be 7 out of how many? 7 out of 31. Good. Take out a calculator and let's get that as a percentage. Probability of Maryland is 5 out of 31. And then I'm going to give you a second to try to figure out the probability that you are in Virginia or Maryland. Okay, so the probability if that's Virginia or Maryland, what will your numerator be? 12, thank you. And still out of 31. Did anybody get that as a percentage yet? Not yet? All right, go ahead and divide it. You're going to need to be practiced at this. Okay. All right, ask questions. Yes. Oh, good question. I'm going to just tell you how many to round to for any assessments, so you don't have to worry about that too much. We'll round to 1 decimal place today, which is going to be 3 sig figs for percentages. All right, you roll 2 6-sided die. Find the probability you roll a 2 and an odd number. All right, a 2 and an odd number. So, probability that it's 2 and odd. All right, what's the probability that you roll a 2? 1 in 6, right? Oh, I get what you're saying. All right, Dolce has a good point. Let's get to that in a second, okay? So let's say, what is the probability that the first roll is a 2? That would be 1 out of 6, right? But we have to save Dolce's thought because that's going to be important. And then what's the probability that the second die is an odd number? How many odds are there on the die? 3. Still 6 sides, right? Okay. So that's the probability that we get 2 and then odd, but couldn't we also get odd and then 2? So we have to take that into account, like Dolce said, and we have to multiply the whole thing by 2. Because it could be 2 and then odd, or it could be odd and then 2. So that doubles our chances there, so we're going to multiply the whole thing by 2. Now remember, a 2 is like a 2 over 1, so this is just going to multiply the numerator. So on top we get 6, and that's out of 36, which simplifies, and we can also get a percent. 16.7. All right. This one says the probability that you roll a 2 or an odd number. Now remember that the or is inclusive, so it could also mean or both. I can't spell that. Remember. I'll try again. Remember. It could be both. All right, and let me refresh myself. Are we talking about 2 rolls still? I think we are. Okay. No, we're still talking about, oh, I get you, okay. We're talking about 2 rolls. So the probability that it's 2 or odd, we're going to be using the formula from up here. So we're using this formula up here that says the probability, one or the other, is probability of A plus the probability of B minus the probability that they both happen, because we don't want to count that twice. All right. So the probability of 2 plus the probability of odd minus the probability that they both happen, to get rid of the double counting. All right, what is the probability that we get a 2 in either roll? I'm going to pause for a minute because I want you to think about that. The probability that we get a 2. So when we built this sample space, we found that 11 out of 36 had 2. And we found 27 out of 36 had odd, right? and then we subtracted the ones that had both, which we actually found right here were 6 out of 36 had both. Okay, so we get 38 minus 6, 32 out of 36. Is that what you guys get? Okay. And we can simplify that. Let's see, let's divide them both by 4. So we get 8 out of 9, or as a percentage, 88.9%. Good morning. Thank you. Okay. All right, any questions? Okay, let's turn it over.
Wait, hold on.
Yeah, I'm waiting.
Why can't we use the 1/6?
1 over 6 plus what?
Plus 3 over 6 minus 1 over 6.
All right, hold on. Stop here. All right, so the way you write this is you write the probability of A given B. And what that means is we know that B happened. Now that we know that B happened, what's the probability of A? Probability A happens given that B happened. It's dependent on another event. Bless you. However, if the events are independent, then the conditional probability is just the probability of the event happening. Okay? So if two events are independent, then it doesn't really matter if B happens. Or if it was the other direction, that would just equal the probability of B. For some reason we have the multiplication rule in 2 places, but this one we'll just put, I think we already put it though. Never mind, we already have it on the front. Alright, this is though important, the conditional probability formula. The probability that B happens, given that A happens, is the probability that they both happen, divided by the probability that A happens. Or you can use the number that's in A intersect B over the number of A. So you can use probabilities or numbers in there. So we're going to build a Venn diagram in example 3. In a class of 25 students, 14 like pizza and 16 like iced coffee. Alright, what's the problem with those numbers? 14 like pizza and 16 like iced coffee. It doesn't what? It doesn't add up to 25, right? Why does it not add up to 25? It's okay. Some people don't like either. Good. And Dolce, can you add to that?
Yeah, like
Some people could like both, right? All right, so we have to figure that out. says one student likes neither and 6 students like both. All right, I'm going to tell you that you actually don't even need that 6 students like both part because you could figure that out. But we have it, so we'll use it. Let's see if it adds up now. Make a Venn diagram. So we have pizza, and we have iced coffee, and we have 6 students who like both. So if 16 like iced coffee altogether, how many go in here? 16 like iced coffee, I already have 6 here, so how many do I put in here? 10. 14 like pizza, I already have 6 here, so how many go here? 8. Alright, and then it says one student likes neither, so now let's see if this adds up. So I have 14, 24, 25, so it works. Okay. One student is randomly selected. What is the probability that they like pizza, that they like iced coffee, that they like pizza, given that he or she likes iced coffee? And this, we'll need to use this formula here. Okay? So I'm going to pause so you can try that and compare answers with your neighbor. Okay, I don't like writing the probability of pizza because they're both p's, right? I'll call it little p though. Probability of pizza is going to be 14 out of what? 14 out of 25, which is what percent? No. 56%? Okay. Alright, likes iced coffee. So you need both of these. Probability of coffee, 16 out of 25, which is what percent? 64%. Okay, probability that they like pizza given that they like iced coffee. So we would write probability pizza given coffee. So that means that the pizza's the B here, the coffee's the A here. What number is going to be our numerator, the intersection of the two? So we want the number that's going to be only in both groups. What number is in both groups? 6. Good. So 6 is in both groups divided by the given part. So the given part here is coffee. We need everybody who likes coffee. So what would that be? 6 over 16. Over pizza? So this is the probability that they like pizza given that they like coffee. So it's the given part that you divide by. So you would divide by the coffee. Okay, so let's think about what this means. We know that the person likes coffee, so we already know that they're in this group. Okay? So all of a sudden, our universe became smaller. Now we only live in the universe of people who like coffee. Okay? So now that we already know that they like coffee, that's our denominator. And then we want to know, given that they're in this group, what's the probability that they like pizza? And that's there. Okay? Alright, so 6 out of 16, we can simplify it. Did anybody make it into a percent? 37.5%? Okay. Alright, last example, and then we're going to do your activity. Your activity, you could work alone or with a partner, but actually I prefer you work with a partner because I only have 15 bags of cubes. Alright, the two-way table describes the members of the U.S. Senate in 2008. Suppose we select a senator at random. Consider the events D equals Democrat while F equals female. So it says find the probability that it's a Democrat given that it's a female. Okay? So, explain what it means. Probability. The senator is a Democrat. Given that she is female. Okay, talk to your group about what number is going to go on the top of our fraction. Remember, the top of the fraction is the intersection of both events. Tell your group what you think. Which number would go on the top? Okay, on the top, what number should we put? Has to be, I heard an 11, very good. Has to be Democratic and female, so that's 11 on top, divided by the number of females, which is 16, very good. Is this what the Senate looks like now? No! In 2018, a ton of women were elected. Okay. 11 out of 16, so let's make that a percent. 68.8%. Or we could even say, you know, I just hate to round just one place up, but you can put 68.8% if you want to be consistent. I don't mind. Alright, so that means that if we are choosing from the female senators at random, we have a 68.75% chance that we will choose Democrat. Alright, probability F given D. Probability that this senator is female given that she's a Democrat. Alright, what's going to stay the same, the numerator or the denominator? I heard both answers. Talk to your group about what stays the same, the numerator or the denominator. Alright, what stayed the same? The numerator stayed the same because we still want the intersection of the two groups, so it's still 11. But this time we're dividing by the number of Democrats, which is 51 in 2008. So 21.6%. Okay, are the events Democrat and female mutually exclusive? Which means like you could only be a Democrat or female. Are they mutually exclusive? No, because there are some that are both. And are they independent? So they're not independent because one party has more females than the other party. So they are neither mutually exclusive nor independent. So the next thing you guys are going to do is you're going to do your dice, coins, and cubes activity. And I'm going to ask you to try to identify somebody that you'd like to work with on that. Theoretical versus actual. So for number 1, for example, on your dice, coins, and cubes activity, and I'm going to end my video so we can talk about this.